Hello, hello, hello. How are we doing today? So we have a nice little question for you. So on average, how many cards in a normal deck of 52 playing cards do you need to flip over to observe your first ace? So if we had infinite sets of a deck shuffled together, then we know that our answer would have been 13, right? Because that's how we do the dice problem. But this is not the dice problem. So in the dice problem, the expected value was 1 by 6 into 1. So you get 6 in the first place plus 5 by 6, and now it is e plus 1. So you solve this and you get e equals to 6, right? Here the problem is it is expected value is changing. This is changing because the first time the draw probability is 1 by 30, and in the second card if you don't draw, then the probability is not 1 by 30, it is improved. So your number should be less than 30, okay, because the options are going away, right? So it's not memory less. If you don't get a 6, then you start from beginning and you count 1. Here the chances of getting an ace, if you don't get ace in the first chance, increases because there are lesser number of cards. So we can solve this in an interesting way. So suppose there are 4 aces somewhere in the deck, okay, and the rest of the cards have 5 places to go. So p1, some will be in p1, maybe 0, it doesn't matter, 0 to some, 0 to 48 actually, and some will be p2, some will be p3, and some will be in p4, and some will be in p5, right? And how many cards will be there on an average in each of these places? So there are 42 cards, and on an average there will be these many cards. So the first ace will be after the expected value is simply average size of p1 plus 1. So that's your answer. That's it. You don't have to do anything else. So 10.6 cards you have to draw, and not 13, before you get an ace. Okay, so we can also verify this using code. So we we shuffle the cards, and aces are represented by 1 4. We do the simulation 100 times, and let's run the code 100,000 times, and we should get something like 10.56, right? And we are getting, and what did we get by probability? 10.6, right? So yes, as you can see, it's a nice little curve, and obviously you will get before. If you don't get any time, then the 49th card has to be. So as you can see, its number of draws is decreasing uniformly, right? You can run it again, maybe you'll get more than 10.6, or maybe you can run it, yes. So this is what you get. Okay, so how about getting the first spade? Okay, so there are 13 spades inside, and so there are 14 spots, and the number of remaining cards is 39. So expected value is 39 divided by divided into how many spots? 14 plus 1. So we should use a nice little calculator. Let me bring it up for you. So the answer is 39 by 14 plus 1. So it should be 3.78. So the answer should be 3.78 for spade or heart or anything. Expected number of draws, not the 4, it should be less than 4. So we can also check that, and we just draw the cards, and a nice little prompt without any error, we can just do it, and we should get something around 3.78, 3.879, 3.7879 is the expected answer. It's taking too long because I'm running it a million times, and then I'm plotting it. Okay, but yes, that should be the answer. We know that is the answer. So I do hope you learned something when the sample space is finite. Yes, we got 7.9, and as you can see, you get a spade in so first spade. Okay, sometimes you took more than 20. Yes, it can take more than 20, right? It can take up to 39. So the 40th card has to be a spade if you don't get any spade in 39, but the probability is like really low. So as you can see, so I hope you understood this, and it's a nice little problem, and we learned something here that if you have a finite sample space, it's not going to be 13 or it's not going to be 4. It will be slightly less than that, because the chance of if you don't get in the first place, the chance of for getting after the second place is not exactly same. It improves. So okay, keep learning, keep being awesome.